Okay. Hello, let's start the talk about Demystifying compilers by writer Yuan. I am Bruno Macabeus. I am a software developer at Pagame. Here is my blog and here is my GitHub, where you can find the source code of the compiler that I show on this talk. And I will talk about several subjects, like the online game Ragnarok, programming languages, and even trees. At the end of this talk, all the subjects will be connected and make sense. Let's go to the main topic about the compilers. But what's a compiler? What's the definition? We have many definitions. For example, a very simple definition is that a compiler is a software that translates a code from language A to language B. But it raises a question. Should A be different than B, or does it make sense a compiler that translates a code from language A to language A? We have a very nice compiler called Babel. It's a compiler that translates a code from JS to JS code around different JS versions or still on same JS version, but generates an optimized code to run faster or lighter. Then it makes a sense a compiler that translates a code from language A to A. But another question, a compiler needs to compile from a language as input, or does it make a compiler that translates from something that isn't a language, for example, a document? We have a very nice compiler called PageDraw, which is a website that translates a document like the web page by layout to web language like JS, CSS. Then we have a more generic definition about compilers. There is a compiler is a software that transforms a data representation to another data representation. There is some way related or equivalent to the first. Okay, but we already have many compilers and languages. Why we need to create one more compiler? We have many reasons. For example, the language that we use has design issues. TypeScript is a JS subset that compiles to JS with the different that implements types, and it's very useful to more complex applications. For example, we have a function create user, and this function receives two parameters, ID and level, but we don't know if the ID really is a number, we don't know all the value levels, and we don't know if the new user is returned by this function. Using TypeScript, we don't have those questions, because the signature of the function has more information. With this function signature, we find that ID really is a number, we discover our value level, and you find that the function does return the new user. Maybe it saves on a database. Another reason is when you are starting a new concept that the current language don't implement. It's the case of Coca. It's a language that employees from Microsoft Research are developing and studying. This language aims to split the values and side effects and defer it at compilation time. For example, we have this code written in Swift, and this function returns an even number. But we don't know if these functions make an I/O, if the return is deterministic, or maybe this function never ends. Using Coca, we don't have any doubts. We only need to reach the function signature. Reach this keyword, and in that, we discover that this function is non-deterministic. In this case, both functions use a random function. Another reason is when you haven't had any issue to resolve, but you still want to write a cool code. It includes esoteric languages, such as Pierre. In this language, you write a code using pixels. Believe me, but this code is a calculator, and so on subtraction. The another reason is when you have a very specific issue to solve. For example, logo has a specific purpose, education. Then it has a very visual feedback, where the student writes a code that the turtle uses to write shapes. A specific purpose language is necessary, a domain-specific language. You can do anything using logo, despite the language design aims to be useful at education. Then we also have the language that I am working, because it has a specific purpose to solve, write macro to online game Ragnarok. Like many of you may already know, Ragnarok is an online MMORPG game, but after a while it gets bored to do the same thing on the game. Then was the solution to make the computer play for you, using a software called OpenKore, about Ragnarok. The OpenKore can make simple actions, but for more complex actions, you need to write some code. And the language to write this code is called event macro. Let's learn more about this language. We can declare two types of instructions, blocks, automacro and macro. In automacro block, we write some conditions to call a macro. For example, if you have more than 4 of this item on inventory, should call the macro half while. A macro is a sequence of actions that the boss should do. Let's print a message on console. Let's move the character on a map. Let's save one variable the amount of an item on inventory. Let's print this amount. And let's go to action when you have more than 4 of these items. Just for curiosity, one important collaborator of this language is Brazilian. And this language has some factors that influence its design. Since OpenKore is written in Poe, event macro is very influenced by Poe. For example, on Poe and on event macro, we have 3 types of variables: a scalar that begins with $, array that begins with @, hash that begins with percentage. Another influence is the implicit interpolation on strings. And event macro runs by a plugin of OpenKore that reads each line. And since the plugin tries to match each line on a regular expression, the language grammar was developed looking forward to facilitate the writing of a regular expression-based interpreter. And take a look at this idea. We can build a compiler for event macro to translate a code from event macro to an OpenKore plugin. With a compiler, we can have an error and warning message at compilation time. As the sun will find an error, the easy to fix the error. And a compiler can generate an optimized code, removing some overhead on the code. And a disclaimer, build a compiler may not be the best solution for your issue. An embedded domain-specific language may be a simpler solution. It's a way to structure a public API of a library as a programming language. That is, it has keywords and you can join them to build routines. For example, you can see the CSS selectors at jQuery and the regular expression in JS as a small language inside of a bigger language. Another example is the Haskell library Metapost. Seeing this code, you could think that it's a language to write shapes, but it's only a library. And another disclaimer, build a new language is very different than build a compiler. When you build a new language, you should think more about the communication between the programmer and the compiler. And build a compiler is more like any other software developing challenge. But okay, I want to build a new compiler. How can I build it? A compiler has some steps. First of all, we have a source code on some language. Then the next step is syntax analysis, transform the source code to a string of tokens, and pass it to a parser to build a structure called abstract tree. The syntax analysis and parser could be implemented on a single step. It's more about an implementation detail. The concept about a compiler where this step isn't split is called scannerless parsing. Furthermore, we have the semantic analysis to check if the abstract tree is semantically valid, and we can pass it to an optimization step to remove an overhead. Then, finally, We have the code generation to build all source code on the target language. In this example, we have a very simple code on event macro. We have a macro sci-hi. We assign to a scalar variable called someone the constant value Macabeus, and on next line, we send to console the mesh high and the value of someone. On the next step, we code build a string of tokens. We find the keyword macro, we find the identifier sci-hi, open brace, and many other tokens. But on my compiler, I didn't have this step because I made a scannerless parsing, which we built the abstract as tree using the source code directly. EST is a way to represent the entire source code on a tree, where each node, where a node is a simple part of the source code. Let's see how to build this EST. In this moment, the compiler checks that we wrote a macro block. Then it adds a node macro that has a true attributes, a name, sci-hi, and a instruction block that is an array. Now it's a scalar assign command. The node has attributes with the scalar variable name and the scalar value to assign. In this case, a text value. And the text value is a literal Macabeus. The next macro block is saved on the next space on array, and the compiler checks the keyword log, and this node has a text value to log. The text value has a high, and an interpolation with the source, the someone variable. Since we have success on build the AST, this code is syntactically correct. Let's go to the next compilation step. Semantic analysis to check if the code is semantically correct. For example, we check if the code tries to read a variable never written. If it happens, this code has a semantic error. To do the checks, we need to build a structure called symbol table. A symbol table aims to expose the information from AST to a more accessible way. To build a structure, we need to pass on each AST node. In this node, we are writing a new macro. Let's write it on the symbol table. You are writing a macro called sci-hi. In this subtree, you are writing a scalar variable called someone. And in this subtree, we are reading the variable someone. Then you can check that all variables that were read were written. Then this code is semantically correct. Let's go to the next compilation step. Optimizations. In this step, we want to remove an overhead and to preserve the code semantic. I implemented two very simple optimizations, constant fold and date cost strip. In constant folding, we want to propagate the context value from variables in order to reduce the variable reading. In date cost strip, we want to remove unnecessary code. Let's start the constant folding. On this line, we can note that we are assigning a variable a constant value. And we are using this value on next line. Since we know this value on compilation time, we can use this value directly. Please note that the AST is simpler now. Let's start the date cost strip. In this line, we are assigning to a scalar variable, but we never read it. Then we can remove this node. Note that we removed main AST nodes. Since we changed the AST, let's start again the optimizations. Constant fold can't note anything special. Date cost strip can't note anything special. Since the optimization can't not change anymore the AST, we finish the optimizations. Another way to stop it is run it for 10 times, then stop. For example, let's go to the last compilation step. Code generation. Since we want to compile this code to run as an OpenKore plugin, we need to compile it to Por code. I have 3 steps on code generation: header code, body code, and footer code. On header, I need to add some boilerplates in order to register this plugin on OpenKore. I also need to import some features from OpenKore to use in my plugin. To do it, I need to pass on each node on AST. Then, if I find a log command node, I know that I need to import log message module. Nothing to do in this node, nothing to do in this node. The next step is the body code generation. To do it, I also need to pass each AST node. Then I need to translate the macro node. On Perl, the equivalent code is substatement. The equivalent code to log command node is message. And to test value node is a literal string with break line. Let's go to the last compilation step on code generation, footer. And it's very simple, just need to add one semicolon at the end of the code. It's important because on Perl, a module needs to finish with a true value, for example, a positive number. We finished the code generation step. And it's all step of my compiler. We saw how to translate a code run on empty macro to an equivalent code on Perl to run at OpenKore. Important, it's a simplification. On AST, code has metadata nodes. I will show more about it soon. A compiler code has many intermediate representations. For example, JAGC, a compiler to Haskell language, has many intermediate representations because Haskell works with a mindset very different than the architecture where all compiler runs. Then there are various intermediate representations that change a little bit to make this compiler easy to build. Also, a compiler could output the final code directly. Is the case of Lua C and Rain. The design of Lua was tough to compile the code on a single step, because it's useful to embed the compiler on a device, because it should be lighter. Let's start the demonstration of this compiler. I wrote a very simple code on event macro to say a random number on game. It's very simple. And we can compile this code to a Perl plugin to run at OpenKore that will generate a very crazy code on Perl, but this code is equivalent on event macro and the Perl code to run at OpenKore. Then you can use this plugin to say a random number at Ragnarok. Then it's working, it's very nice because we can write a code.
Use security connections.
I found my mouse. Okay, but how is the code of event macro? I write the compile use Elixir. I chose the Elixir because it's the hype, and also because I want to learn more about Elixir. Also, this plugin has 2 features very useful to a compiler. Pattern matching, which is useful to identify what's the node, and Elixir works very well with recursions. It's important because we need to pass the AST and each code be implemented with a recursive code. Okay, let's see more details each compilation step. Let's see more details the parser. To write a parser, we need a grammar to specify how our language should be written. We have many ways to write a grammar. I will talk about 4 of them. Regular grammar is a very simple way. An example of regular grammar is a regular expression. A moment where it's useful is when you need to pass a command in a CLI. We could have a command to move to a position at a map, and the map name is optional. We may write the regular expression to match this command. It's a very simple solution to a very simple issue. Because regular grammar is a very simple grammar, it has some limitations. For example, we can't match an arbitrary sequence of commands, then we can specify a next code block. For example, in GraphQL, we can have a field inside of another field. We can specify each using only regular grammar. We need something more powerful. Then we could use an EDSL, which is a small language inside of a bigger language, and we could use the EDSL to write a grammar. We could write a grammar using EDSL to match the previous command instead of using a regular expression. Then we will have a grammar like it. Another way is a context-free grammar, which we have a symbol set and the transformations for each symbol. An example of CFG is BNF. On the left side, we have all symbols, and on the right side, we have the transformations for each symbol. Then, by this grammar, we can say that A9 is valid text, and WW isn't a valid text. We also have the past expensive grammar, and such like of CFG, we also define a symbol set and the transformations for each symbol. Wire is the same grammar, but using PG. Okay, CFG and PG are very similar, but we have 2 relevant differences. Firstly, the notations. It's very easy to note. The CFG notation is very different than PG notations. For example, you can use regular expression on PG, and a relevant difference is the whole interpretations. Because on CFG, the order of whole doesn't matter, but on PG, the order of wholes is very relevant. Think a situation where I could use the whole A or B to parser. If I am using CFG, the parser will crash because it doesn't know how to work with ambiguity. But if I'm using PG, the parser will say to use the whole that came before. Then the order of the whole matter, and I need to give more attention about if I'm using PG. Okay, using a grammar, we can specify how is the syntax of the language, but we need an algorithm to run this grammar. I will talk about 2 popular algorithms. The main difference between them is the interface. Using parse generator, by a description written in PG, BNF, or anywhere else, it will be compiled to generate a parser to use in a compiler. Then the compiler can use this parser to build the AST. And a parse combinator has another approach. We write a very simple parsers, parse A, parse B, parse C, and join them to build a more complex parser. Very nice, but how can I run this algorithm using Elixir? We have very nice parse combinator library called Combiner. In this library, we write a grammar using EDSL. And it gives an approach scannerless parsing, which the compiler will read the source code to build the AST directly without a tokenized step. And as well you can see, the library is a toolbox with many very simple parsers. And you need to remember many of the very simple parsers you join to build a complex parser to your language. Okay, let's see a practical example. Write a parser for event macro command. Where is the push command? Semantically, it is used to add a text to an array, and syntactically, it has a keyword push, an array variable name, and after a comma, a text value. We should pass this command. Now we have here a very complex parser of push command. There is a sequence of string push, open parentheses, an array variable name, space, a comma, space, and finally a text value and close parentheses. There is very complex parser. But this very complex parser uses a simpler parser to describe the array variable name, which is the sequence of an at and an identifier. And the identifier is a simpler parsing, which a sequence of character ending space or new line or comma. And the push command also uses the text value parser. This parser is similar to the identifier, but you can interpolate with variables. Then the idea really is the same as I said. We have very complex parser, push command, and this parser uses a simpler parser, array variable, that uses the more simpler parser, identifier. Push command also uses the text value, which uses the variable parsers. After running the parser, we need to map the result to save it on the AST. We can map it to a structure in Elixir because it will be easy to work in the next steps. In this case, each structure is a node on our AST. Okay, let's go to pass a very different thing, a code block. In this language, we have macros that has a code block. It also has a if that it also has a code block. Okay, they are similar, right? Then the pass are also similar. Both use the macro block parser, and each maps the code block on the structure use the same key to work on same way on next compilation steps. And the macro block is very nice. It is a set of passes and it tries to pass using doc command. If it fails, try using log command. If it also fails, it tries using call command. If all passes fail, then a syntax error arises. Let's go to the next compilation step. Semantic analysis. Like I said, the symbols table is important to expose the information from AST by a more accessible way to next compilation steps. Then I wrote a function called build symbols table that will receive the AST to pass its node. I recursively call the function symbol table. Then if I find the macro node, I will write at the symbol table that I have a macro with this name and this code block. If I find a list of nodes like a code block, I will map each command node from this block. If I find the calc node, I will write at symbol table that I read a macro with this name. If I find the push node, I will write at symbol table that I write as some variables and I read some other variables. This is the idea of how I build my symbol table. But okay, I build a very complex structure. I need a way to read it. Then I have a module called symbol table that has some helper functions. Functions like list the marks read and read, list the variables read and read, and other functions. To read the symbols table, I used a lot of the access library. It's useful to write routines to access a complex structure. Okay, now I need to use my symbols table on some validations. For example, let's check my macro because I can't try to read a macro never written. Then I have a module to validate this whole. This gets the symbols table. On next step, from the symbols table, each lists the marks that we read, each lists the marks that we written, and it checks the difference. We can note that we are trying to reach a macro never written. It's bad. Then the validation raises an error. Okay, I spoke about the past and semantic analysis, and both steps raises errors. How I handle the errors? Do you remember the macro block parser? Then, if all passes fails, a syntax error is raised. Something fun is that the function that raises the error is another parser. And it says the line and the column that the bug happened. Then I can have a very nice error message like it. For example, the programmer forgot to write a close parenthesis. Another error that the compiler raises is a semantic error. To show a good semantic error message, we need more information on the AST. Some nodes called metadata. To build this node, when the compiler is passing a code, for example, log full, we have this parser. It uses a macro called parser command. This macro has a sequence where call the get metadata function. There is another parser. That it returns the line and the column from the source code. Then instead of give a very simple AST like it, we can have a more complex and useful AST. Then I can show exactly where a semantic error happened. The compiler has two types of semantic errors, a warning and a fatal error. A warning is something weird but not wrong. Right? For example, write a variable but never read it. Also, I have a fatal error where something is wrong. For example, try to read a variable never written. Let's go to the next compilation step, optimization. Now I want to remove an overhead from the code. One optimization that I made on the compiler was the constant folding. This optimization wants to propagate the constant value null at compilation time. For example, this code will be compiled like this other code. You can note that we have less variable reads. Then at the symbol table, I build a context about the variable's value at the end of each macro. Let's optimize the macro. At the context as the arrow, we know that the value of name is Macabeus. Now I have the full and bar at the context. Please note that we don't know the bar value at compilation time because it needs an I/O. Then we can optimize the full, but can't optimize the bar. Now we need to update the name variable, and we can propagate the name value. You can see the code of this optimization on my GitHub. Nice. Let's go to the last step. Code generation. Since I need to compile from every macro to a plugin to run at OpenKore, and OpenKore is written in Perl, let's compile it to Perl. I split the code generation in 3 steps. Code generation to the header, to the body, and to the footer. Please note that this step is just main array concatenations, where each part of this array is a Perl code. I will generate an array with depth n. Then I use a flatten to make this depth 1. And I use a join to get a string with the end code. Let's talk about the header. One thing that I need to do is make the body place to resist the plugin on OpenKore. It's just add some string on the array. Another work is to find which variables are written to declare global context at plugin. It's important because in every macro, variables all are global, while in Perl, variable has scope and needs to be declared before to use. And another similar work is to find what modules from OpenKore you need to import. To do it, we just need to pass at AST node. If we find the log command node, we know that we need to import the module log message from OpenKore. If you find an array variable node, we know that we need to declare an array with this name. Then add this result as the array. Also, we need to find which macros are written to do each callable by the CLI. To do it, I use my symbols table, use the function list written macros. Is the code. On header, I make these 4 things. The next step is the generate the body code. In some way, I need to translate this every macro code to this per code. Like I said, we have some parsers that generate an AST. Using this push command, we will get this AST. Let's pass each AST node. At the push command node, we will start to generate the end code at array. We have push, something, comma, something, and semicolon. Let's call recursively all the generate function. At this sub-tree, we will generate the array variable reference. In this case, the code will be at values, and the code generation to the test value node is a little more complex because we need to handle the variable interpolation. But in this case, will be FOO. Then we just need to use the flatten and the join. Then we have the equivalence code in PO. The push command is very similar between every macro and PO. But we have other commands that are different from these languages. For example, the hand command that generates a very different code in PO, but the idea is the same. Finally, the last code generation step is the footer. Like I said, we just need to add one semicolon as the array. We finish our compilation steps. Finally, I really want to thank Pedro Castillo because he helped me a lot to code the compiler and to make this talk. There are some image sources that I use in this talk and some links to learn more about the subjects that I spoke. And more links, I really recommend this second link. It's a manual about parsers. And I present the same subject of this talk as the YouTube channel of the company that I work for, Pagami Talks. These talks are in Portuguese and have more topics like test and recursive grammar. I record an Ask Cinema where I add a new comment in the compiler and I explain each step. Finally, you could see at GitHub the source code of the compiler that I show here, microcompiler. And thank you.